It's great to be here at Unite in Los Angeles. My name is Arthur.
My name is Vladimir.
And we're going to be talking about Unity, machine learning, and games today. So just to kind of start with some setup, some of you maybe are unfamiliar or somewhat familiar with the role of machine learning in games. Kind of quick show of hands, who has used some of the tools from Unity that have to do with machine learning before? Nice. ML agents. Great. We're going to be talking a lot about that today, but not only that. Who's maybe less familiar with machine learning? Show of hands. Great. So we'll be explaining some of that too. So this is a couple examples to kind of get us thinking along the right way, which is what's some use cases where we might want to utilize machine learning to get AI agents in games, as opposed to doing a more traditional approach. So here we have the games of Dota 2 and the traditional Chinese board game of Go, both of which are games that humans have dedicated hundreds and hundreds of hours of learning how to master, that humans love to play, and that are difficult to hand code solutions to, difficult to create bots that are challenging for the best human players. Now, what do you do when it's impossible or difficult to create a bot that's challenging for human players? Well, OpenAI and DeepMind, two of the biggest research groups in AI, took the approach of training machine learning models to be able to play these games. And they now have bots that are able to compete with the best human players in these games. Now, what we want to do at Unity is take these same kinds of technologies and put them in an open source toolkit that everyone can use as part of the Unity editor, and that you don't need a big team of researchers and hundreds of thousands of dollars to solve problems with. So that was the motivation behind ML agents, Unity machine learning agents, and our open source toolkit, which we're going to be talking about today. Now, this is the general workflow. So you set up a Unity scene, you insert the ML agents SDK into that scene, and then you set it up in the way that I'm kind of going to describe. You then move on to training the agents in that scene. Now, this training of agents is somewhat different than traditional hand coding agents, and we'll talk about the ways in which you have to think somewhat differently when you're training agents. And then lastly, I'm going to hand it over to Vlad, and he's going to talk about actually taking these trained agents, putting them in games, and having them run in performant ways on a number of different devices. OK, so step one, setting up the scene. So I've said the word agent quite a few times. And anyone who's done AI programming is going to be somewhat familiar with agent. But here, agent has a very particular meaning in our context. So just want to get everyone on the same page. So agents interact within the environment. And in this case, the environment is going to be a game. And at any given moment, that environment is in a certain state. And the agents in that environment can observe that state, collect these observations, and then use these observations to take actions. And now this mapping between the observation and the actions that the agent takes is called a policy. Now, this policy could be any kind of function. You could come up with a policy that says completely ignore the observations and do whatever you want, act randomly. You can also come up with principled policies. What we're interested, though, is learning the mapping between observations and actions such that we get out a behavior that we want in a game. OK. Now, why would you want to use these agents in your games, and what are the kinds of agents that you might want to train? Now, in our team, we think about this in terms of three different categories. We have player agents, and these are agents that play the game just like a human would. Then we have non-player agents, and these are agents that are your traditional NPCs in games. And then we have what we call invisible agents. And these invisible agents are kind of like the game master, so to speak, that can set the rules and change the parameters of a game. Now, for each of these, there are specific uses we think that ML-driven agents can be applied to. So for player agents, that means things like game balancing, game testing, having an AI agent play the game as if it were a player to try to find bugs in that game before launch, things like this. Then on the NPC side, I already showed everyone here a couple of examples where you can train agents to either be adversaries or companions in ways that are in games and scenarios that are more complex than what you might traditionally find. Then lastly, in the case of the invisible agent, we can think about this along the lines of actually adjusting the parameters of a game to dynamically change the difficulty, for example. Okay, now this is a diagram which anyone who's used ML agents is going to be a little familiar with, but this is the high-level way in which the specifics of the objects that you add to your scenes work. So we have the agents that are actually in the scenes, interacting with other game objects, other entities in your Unity scene. They're the things also taking in observations and acting. Now, what actually does the decision-making, what actually contains the policies that map these observations to actions for these agents are what we call brains. And these brains are conceptual entities that contain everything about the policy. And we can have, in any given scene, multiple different brains with multiple different agents connected to each of them, so that we can get a lot of interesting multi-agent dynamics going. Then lastly, we have this notion of an academy. And when you add an academy into your scene, you're turning your scene into an ML agent scene, where you can then export it for the training process. Which brings me to the training process. So I mentioned at the highest level on that other slide that we're training with Python. Here I have an image of Python there and TensorFlow. So we're using TensorFlow to do all of the training. That kind of happens behind the scenes. What you as a developer might need to think about, though, are the kinds of training methods that you're using and the kinds of learning signals that you want to provide to your agents to have them learn the behavior that you want. So the first kind of learning signal and the first kind of training method is reinforcement learning with a reward-based signal. Now, this is the game loop, the learning loop we like to think about in the context of reinforcement learning. And what this really is this iterative process whereby an agent acts in the environment, receives some kind of reward that you as the developer have provided for it, and then takes some actions. And based on whether or not those actions led to good or bad outcomes, the reinforcement learning algorithms then attenuate the actions such that things that led to bad outcomes happen less often, things that led to good outcomes happen more often, until the behavior of the agent is optimal. So this involves explicitly defining rewards. This involves a lot of trial and error on the part of the agent, and this can often lead to the ability to perform some task that is optimal. And in many cases, optimal can sometimes mean superhuman, or at the very highest level. So to kind of make this more concrete, I'm going to show an example of one of the very first things I worked on when I first joined Unity, which is this nice Frogger-like game. So in this scenario, we have the agent is this little chicken, yellow bird thing that crosses the road. Getting presents provide positive reward. Running into a truck provides negative reward. The agent's actions are moving in any of the 4 directions. And the observations are actually the pixels on the screen. So in this case, it's a little harder. We may have thought of any sort of interesting other things to give the agent as observations, but we said, OK, let's just do the most straightforward thing and see what it learns. So I'm going to show a video of the learning process using a very simple reinforcement learning algorithm. So at the very beginning, the agent's policy is random. The mapping of observations to actions has no sort of intentionality to it. And so what you see is the agent moving around in essentially circles. But every once in a while, it'll hit one of the packages. It'll get a positive reward. And whatever series of actions it took to run into that package is now going to be reinforced. And it's going to be more likely to do that kind of thing in the future. So what you see is after a couple of hours of training, the agent is able to get better and better and hits the trucks less frequently. Now, what I just showed you was the random training, intermediate training. What you're seeing now is the optimal learned policy at the end of the training process. And the agent's gotten very, very good at picking up the packages. Even tricky moves like the one you're about to see. Yeah, like that one. It's just, sees all of the trucks and goes right past all of them. So this, for us internally was a really great demonstration of the fact that these tools with really simple reward functions, really simple sets of observations and actions can be used to learn desirable behavior. Now, there's this other way of providing a learning signal, and that's through imitation learning. And there may be cases where a reward function just isn't exactly what you want. So it may be simple to say packages are good, getting hit by a truck is bad, but it's very difficult, for example, to come up with a reward function that corresponds to encouraging an agent to do a backflip, for example. You know, maybe you say land the backflip is +1, but what if it never even gets close to landing a backflip? How do you iteratively kind of encourage that kind of behavior? This is where things like providing a demonstration makes a lot of sense. And especially as game developers, many game developers are also game players. Many people, when they make a game, are thinking about how the player is going to play. So simply providing demonstrations of how to act in any given game is, I think at least, an intuitive way of helping to train an agent. So what I'm going to show here is a little demo that we put together using a kind of like mini scene from the game Anti-Graviator by Cybernetic Walrus. What we have on the left is myself playing the game, and I'm the human player. On the right, we have the machine, which is the ML agent's agent that's going to be learning. So at the very beginning, we're starting out. The agent has completely random behavior. And in real time, I'm going to be providing demonstrations of how to race along the track. And the agent is going to be learning from those demonstrations. So let's start it. So you see at the very beginning, the agent's behavior essentially is random, or here it corresponds to not moving at all, and it just runs right into the wall. Meanwhile, I'm going through the track, hopefully pretty well, to the best of my abilities at least. I'm not crashing, so that's good. And what we find is that very, very quickly, the agent is starting to go through the track correctly as well. And in this case, the observations are corresponding to just a few ray casts in front of the race car. And after only 5 minutes of demonstrations, which is almost none of my time racing around the track, we have an agent that's also able to make it all the way around the track without crashing. So really, really quickly, without writing any actual lines of game AI code, we're able to get the desired behavior out of a learned agent. And those are kind of the two high-level methods that we can use. Now I'm going to dive a little bit more into the toolkit and show you a few more examples of what we've been working on to kind of demonstrate some of the capabilities. So what you see here is a high-level image of a bunch of the example environments we provide. So I mentioned it's an open source toolkit. You can download it from GitHub, and all of these example projects with all of the code and comments will come with it. Now we can start really, really simple. We have a 3D balance ball where the agent controls the platform. The goal is simply to keep the ball from falling off the platform. What we can do, though, here is demonstrate very, very simple multi-agent capabilities, where we have a bunch of agents all within a single scene, all gathering data simultaneously, so we're able to train very quickly. And then when it's time to actually run the models, the agents can do the balancing quite well. Now, what I've showed you so far is kind of like straightforward reinforcement learning, imitation learning. You define your signal and you learn. But when we move away from this defining the behaviors specifically to training, learning, ways of thinking about things, there are other interesting augmenters to the learning process which come up. One of these is the idea of a curriculum. So a curriculum is relatively intuitive for most of us. You start learning easy things, then you learn slightly harder things, then you learn slightly harder things. And at every step, you build upon what you've learned to achieve something you couldn't do before. So we can apply this directly in the context of machine learning. So here we have a really simple case where we have the goal of an agent. The agent here is the blue cube, is to arrive at that green button over there. Now, if we start with the most difficult version of the task, with the tall wall, in this most difficult version, the blue cube has to push this orange block to the wall, jump on the orange block, jump on the wall, get to the button. Now, that's a little tricky for it to do with no experience, because that's a very specific sequence of actions it has to learn. So we can start by setting up a curriculum where there's no wall at all. All it has to learn is to run and jump on the green button. Then we can slowly build up a wall, have a wall that's easy to jump over, and then eventually have the wall that you have to push the block over to. And by following through with this, we eventually get an agent that's able to easily use the block to get over the wall. So this is kind of, we're hoping to encourage, is this new way of thinking about getting behavior out. where you think in terms of what is a reward function, what is a curriculum, what are these ways in which I might want to teach my dog, for example, how to do something. Now, as I mentioned, we've also been thinking very much multi-agent from the start. So I just want to show another multi-agent demo we put together where we train this kind of like little 2v2 soccer game where agents are either offensive or defensive. And in this case, this corresponds to having two separate brains, one brain for offensive behavior, one brain for defensive behavior. And you can see here them all playing together, playing very nicely after what is only about half an hour of training. And now, along these lines of thinking about learning, we can start to introduce other concepts that kind of come not so much from computer science, but maybe come more from psychology even, which is concepts like curiosity. So we have an agent that's learning. We have an agent that's exploring an environment. How are the ways in which we can augment that reward signal or that imitation signal with other useful information to help it learn interesting things? So one of the experiments that I had worked on over the summer was on implementing this great curiosity-driven exploration. And what this corresponds to is essentially having the agent reward itself for finding new parts of the environment, discovering new things about the world, essentially. So to test this, I set up this harder to solve task in which essentially the agent has to find this golden pyramid with a big brick at the top, knock the pyramid over, and get the brick. Now, this is more difficult because only the brick is rewarding, and the environment itself is a big big grid of 9x9 miniature rooms. So you have these 9 different rooms. Each of them either is going to have this stone pyramid that you can't knock over, a switch, or an empty space. Now, once the agent, the ideal behavior, if you were playing this, any of you could figure it out very quickly, would be to move around the rooms, find the switch, hit the switch, that spawns the pyramid, find the pyramid, knock it over, get the gold brick. Now I'm going to show you what happens in different contexts. So if we take our traditional reinforcement learning system that doesn't have any curiosity, it's very difficult for it to do the full sequence of the brick. And what it learns after about 1 million training steps is to do nothing. Or to run into the wall, I guess, yeah. And so in the absence of a meaningful learning signal, what's learned is, run in circles. Now what I can show is if we say, okay, no external reward, nothing for getting the gold brick, but only this internal learning signal, what kind of behavior is going to come out? Oh. You might have to press it.
Yep.
Thanks, Vlad. So what we see here is the agent isn't exactly doing the right thing, but the agent has learned to move around the space quite a bit better than the other one. So it's not getting to the goal, but we shouldn't expect it to get to the goal because it wasn't trying to get to the goal. What it's essentially learned to do is move around, go to 4 different rooms, play with some stuff, try to knock over some blocks. Now, when we combine the extrinsic signal of the gold brick is great with the intrinsic signal of let me explore and discover new things, we find an agent is able to very quickly learn the task and use the switch, get the pyramid, knock over the blocks. So in this new paradigm, our thinking is that there are all of these building blocks, all of these kinds of learning signals, and we want to provide everyone here the tools to mix and match, combine them for their use cases, and then apply them to get the behavior out that they want in their games. And now this brings us to the important point of once we've set up a game, trained our agents, they have the behavior that we want, how do we actually ship that game? How do we actually give people easy ways, performant ways to put these agents in their games? Now, people who are familiar with ML agents have known that we've provided a solution through TensorFlow Sharp, and that's worked with a few platforms, and it's been kind of like unofficial support. But today, Vlad here is going to talk to you about the future of inference and our plans to kind of have the true Unity solution to having agents in games. I'm going to hand it over to him.
Hey guys, like Arthur mentioned, after you've trained your model, you will need to embed it in your game and perform inference. But what is essentially machine learning inference? So for those of you who are not coming from any machine learning background, machine learning inference is the process of running data through the trained model in order to receive the results. So for example, if we're dealing with an image classifier, we can feed the model, for example, an image of Papa, and the result will be a classification of this image correctly as Papa. In the example of ML agents, the input can be observations or the image of the scene, and the output can be whatever action the agent needs to perform. So this is a very complex operation. Why is it complex? Let me show you just a simple example. This is a model that is used by one of the ML agent games that I will show you in a bit. It's not a complex model by any standards in the machine learning world, but still it has 26 matrix operations that happen every few frames, 6 multiplications, 4 inner products, 16 element-wise operations. Now imagine doing that for 10,000 agents in a game running 60 frames per second, and don't forget physics, don't forget graphics, and anything else that your game needs to run. And of course, we would like to run this on all the platforms that Unity supports. We are kind of priding ourselves in the way that you can develop once in the editor and then deploy on all the platforms that Unity supports. Some platforms provide high-level inference libraries and abilities, like, for example, WinML on Microsoft platforms, CoreML on Apple platforms. Some platforms don't provide anything, or maybe even some low-level primitives for math that we can take advantage of. In order to perform inference efficiently from power standpoint, from speed standpoint, from size standpoint, we would like to utilize all these low-level and high-level optimizations and provide them to you as game developers. So we would like to announce about a solution that we're working on, the Unity Machine Learning Inference SDK solution. It is a generic platform-agnostic API that game developers can integrate with once. It will allow us to run inference on CPU, GPU, any other specific devices. A lot of hardware vendors are working on hardware acceleration devices for machine learning, so we're planning to take advantage as much as we can of those accelerators. And of course, it will be fully integrated with ML agents, so it will work right out of the box with models trained with ML agents. So to show you a small example, some of you may have already seen Papa the Corgi. So this is a little dog that was trained with ML agents, starting from control of its limbs. So essentially, it learned to walk from scratch with ML agents. The cuteness is not hard-coded. It's completely artifacts of the training. And it also learned to go and fetch the stick and bring it back to the user. So, hours of fun. Yeah, sometimes he falls and topples over, and then we can feel sorry for him, but looks like he's succeeding. But what is better than one puppy running around? It's many puppies running around. So here we have a small demonstration. We have a puppy running after a robot carrying bones. Let's see if you can grab one. Come on, go, go. Yes, and he grabbed one. But let's give him some company and some competition. So now we have 10 puppies running after the bones, competing with each other. Oh, he fell. Yeah. Yeah, it's a dangerous world for puppies. But what's even better than 10 puppies, it's 50 puppies. So here you can see we have average stats running. So we're running inference here every 4 frames for all of the 50 puppies, and it's still not fully optimized. We're still optimizing this, this scene. But essentially, you can see on average 3, 4, 5 milliseconds for all the 50 puppies for performing inference. And we're running at 59 frames per second with CoreML on iPhone 8. Thank you. A lot of platforms, like I mentioned before, they provide some kind of high-level or low-level libraries for performing inference, or at least math. But a lot of platforms don't do that. Like, for example, PlayStation or Nintendo, other consoles. So we also have a homegrown cross-platform inference solution that was built by the Unity research department, Unity Labs, and it will be running under the hood of the machine learning inference SDK. It is utilizing all the newest stuff in Unity, like, for example, automatic vectorization for SIMD with burst, or IL2CPP on older platforms. It is using the job system in order to utilize all the cores of the target device. It can run on CPU with an optimized CPU implementation, or on GPU with Unity compute shaders. And it's, of course, tightly integrated with the Unity rendering loop. And as another example, I would like to show you an upcoming game called Jelly Ball by What Up Games Studios. So this game, it has a bunch of agents running around. The goal of these agents is to collect the red diamond sugar cubes and return them back to their base. The movement of the agents is completely controlled by a machine learning model trained with ML agents. The attack defense strategy is more traditional AI, but all the movement was trained with ML agents. And inference here is running with a Unity homegrown solution, and we're running on GPU on Xbox One, where the actual image of the scene is being passed from the rendering engine directly into the inference engine from GPU to GPU in order to be even more efficient. All right, thank you very much. If you would like to learn more, we have our GitHub repo that you can download all the examples from. Feel free to stop by our booth. We're down at the expo level. And of course, we're hiring. So we're looking for mobile engineers, machine learning engineers, and game developers. Come chat with us. I think we have 15 minutes for questions. There are 2 microphones there and there. Thank you.
Hi.
Yeah.
First of all, awesome work. Huge fan of the machine learning work you guys have been up to. I noticed that in some of the agents, you're feeding the pixel buffer, the game view, into the agents for learning for the information. And sometimes it looks like you're using raycasts with some of the basic data that gets back. Do you find that you're able to have agent brains that are more flexible and reusable with the raycast? And is there like a performance quality trade-off between the two that you found?
Yeah, so it's definitely the case that a lot of the research that people do outside of gaming on this, they like to use pixels because pixels are kind of the most general representation. You can put anything into an image, and that's the thing. I think in many cases, if you as a game developer know about your underlying game state, then feeding that information in can often be more useful. Because, for example, if you want to get out what is in front of me, is it a truck or is it a tree? You can either have a model learn to take an image and interpret that, or you can just feed that in directly, right?
Thank you.
Mm-hmm.
Yeah. Hey, so in the example you did with the pyramid, collecting the gold at the top, how would you handle a situation? Let's say it has like multiple goals. Like if it was defending something or it had to collect something as well as try and get that. How do you balance multiple things that are completely different objectives?
Yeah, so there's a number of approaches. One is if at different times you want to follow different goals, you can just simply train different models and have some sort of switching mechanism between them. Though if you wanted at the same time to balance between different behavior, the most straightforward way would be to correspond to kind of the magnitude of the rewards. So whatever's the most important thing, you'd assign the highest magnitude to, and lesser important things, less magnitude to. And then based on the ratio of those things, the behavior would try to optimize them in correspondence. Does that kind of answer your question? Mm-hmm. Oh, yeah. OK, great.
I think it's in the same kind of vein, the same golden pyramid example. How do you define kind of curiosity in terms of the intrinsic reward? What is the agent looking for, and how does it get rewarded by the kind of curiosity metric you were talking about?
Yeah, so this curiosity metric, the explicit way it works is that the agent is predicting what's going to happen in the future and what it's essentially going to observe in the future. And to the extent to which what it observes in the future is different than what actually happened, what it predicted, then it's a bigger intrinsic reward. So essentially, it corresponds to kind of like surprisal, you might say, or something like that. Mm-hmm.
Cool, thank you.
Yeah, thanks for your question.
I'm new to the ML agents entirely. So for a newbie, how exactly are you defining? It sounds to me like you're making so many assumptions about, well, you know, you can move and you can touch objects, and he explored new things. And I'm just like, how are you representing that in some sort of code system that's like, this is a new thing, and how does it know to save that state? What does that even mean that you're saving that state, that is persisting, that like I bumped into a wall? Is that new? Like I'm disconnected on how a Unity app and ML agents and how you'd map your whole game state into these different quantifiable things.
Yeah, so I would say we have 2 hands-on sessions on Wednesday if you want to kind of like get a deep dive into what the actual code and workflow really looks like. I can say at the high level, there are explicit abstractions for observations and actions, and you as a developer map whatever relevant variables exist in your game explicitly into observations that the agent has access to, and then you map the actions that you get back explicitly into whatever effects you want them to have in the world. So it's kind of like this entry and exit point for behavior, and then you have complete control over what goes in and comes out.
So I'm sorry. So the agents then you have in the library, it has the ability to have already the concept of you'll have your game state and whatever your game does, and then in addition to that, you'll be able to implement, these are my observations, these are the actions you can take, and then you allow, at that point, the agents can then connect and do the actions and do a series of actions. And because they're doing millions and millions and millions of these things, who cares if they're intelligent or not? The idea is that if I take this series of actions based on this game state and these observations, and then this next thing happens, then I can be looking forward to that different new observation or new activity. So you really just focus on the observations and the actions.
Yeah, that's exactly right.
Define a policy.
Mm-hmm. So the agent's entire world is filtered based on how the developer defines what the observations and actions are.
Awesome. I look forward to that. Thank you.
Yeah.
Guys, thanks for the talk. I'm curious about what the format of the output data is. It seems like this would be really interesting to mix with like an online game and get data, training data from like all of your players to see what the best people are doing or like interesting strategies and stuff. But if it's just like a blob of binary data, I don't know that it would be easy to combine like all these sources into one training data. So I'm curious if you could talk about that.
Yeah, so it's the case that you have to be able to convert whatever your game state is into a numerical representation. And so if you can convert it into a fixed length numerical representation, then you can use it in the system.
Okay, cool.
Okay, this is kind of a random question, but in the dog example, I noticed that the dogs, once they were on the track, you know, they would ignore where the track was and could run across the grass. And almost none of them got a bone. And so one can imagine that one of them would get a wild idea and cut across the grass and intercept the bone on the other side. Clearly they didn't do that, but what I'm curious about is what would you have done if you wanted to be that, for that to be a possible strategy?
Is that for that to be a possible strategy?
Yeah,
or
I mean for them to
strategy?
learn to do that. When do you just cheat altogether?
Well, you can probably penalize the agent if he escapes from the racetrack, and then he will learn to stay on it.
Yeah.
Yeah, so I would say that explicitly the dogs here were trained to simply run in the direction of the goal, the pre-specified goal, align with the goal as best as possible, and go as fast as possible towards that goal.
It makes perfect sense. And by the way, congratulations on a great talk and really cool work. But
Yeah, thank you.
I was curious about how are you learn?
Hello. This is actually building on what he was just talking about. You mentioned before that you developed curiosity, I guess, in your that pyramid example. Is it possible to do cleverness and develop something where you're surprised by the outcome? So going back to the dog example, the goal is to basically get a bone. So what if you can program, or what if you can train the dogs to the point where one dog actually steals it from another dog, rather than picking it from the pile? Is that ever possible?
So that's actually very similar to what's happening in the Jelly Ball game. So there are a bunch of agents that are running around, and they have two main strategies to get the sugar cubes. One is to actually collect them when they're flying around, and another is to hit another agent and steal it from them. So it's definitely possible. It's just all a matter of crafting the correct reward function.
Okay. And my second question is, how deterministic the behavior result is? Like, how deterministic is it? For example, if I were to run 2 simulations of 1,000,000 times each for the same robot, or whatever it is, the same observations and actions, are they both going to end up with the same behavior?
For training, or after you were done training?
Training.
Training, I'll probably pass it to.
So it's we have the capacity to set the seed in the ML agents training process. So if you provide the same seed, you'll have the same initialized network, and you should get the exact same training results out.
Yeah, and on the inference side as well, you're essentially passing all the data in. So you're controlling the random seed of the data you're feeding in, and it's totally deterministic, up to, of course, floating point stuff.
I see. Cool. Thank you.
Hi. Has your team attempted to bootstrap reinforcement learning with imitation learning?
Yes, yes. So as I was talking as if these were two different things. I think in a lot of cases, it's actually going to make sense to combine a sparse reward with a dense demonstration signal. And this is the kind of work that we're actively working on right now.
Thank you.
I have a question about the basically overall kind of roadmap on the training and model side. Are you guys going to be full on just PPO, or are you guys experimenting with other policy network? And then the second question is about double agents with mixing with continuous outputs and discrete outputs. Is that in the work?
So I would say, for those who are unfamiliar, the current training algorithm we use under the hood is called PPO. It's quite good, very robust, stable, deep RL algorithm. We have the intention to kind of move to more distributed training setting in the future. For right now, I think it's probably going to take a while to unseat PPO as being the most simple and stable system. To your second question about combining discrete and continuous actions, we introduced what we call multi-discrete recently, where you can kind of a little bit get the best of both worlds. So you have multiple discrete actions, but you have different axes upon which you can take them. It may be the case that we explicitly combine them in the future, but I think we can actually get a long way with the multi-discrete.
Oh, okay, thanks.
Hi. So during the talk, you sort of mentioned inference and training as sort of two separate things. I'm just wondering, do you support or do you plan to support post-deployment training? So as opposed to just baking the inference into the shippable product, is it possible to have a game in which the agent is still learning from the player or from observations, et cetera?
We have thought about it. From our analysis, we saw that a lot of the cases where we would like the agent to train post-deployment are actually doable by collecting data and training offline on a bigger machine. So we currently don't have any plans, but we might in the future.
Okay, thank you.
Hi. Sorry, ooh, that was really loud. My bad. So I've watched a few things with like Dota 2. I know that they've had a lot of bots that they've been training whenever they're doing learning against players, and they've actually had those bots demolish the teams once they've learned enough. Do you guys have any way for us as game developers to kind of put a handicap on the bot so that they don't completely demolish our players over and over and over? Because if they're trying to learn how to best reach an objective, I'm going to assume they're probably better than us in reaching those objectives quickly sometimes. So do you guys put any sort of handicaps in, or how do you deal with that?
Yeah, there are a number of possibilities to approach this. It's something that we really understand is very important because really no one wants to play against an agent that they're always going to lose against, right? I think one really immediate way is simply, the agent gets better and better over time, and it's very easy to snapshot these agents during the training process. So say along the way from being completely random to being superhuman, you get all these snapshots of intermediate behavior, and it may be the case, 75% through the training process, that behavior is just the one that you want, and it'd be very easy to grab that. It's also the case that because these networks are entirely based on just floating point numbers, it's also very easy to linearly change how deterministic or random they are. So, say it has perfect deterministic behavior, you can scale that down, say 75%, 25% take less optimal actions, and maybe that corresponds to less perfect behavior. And then I would say the third thing is a little further down the road is there are a lot of exciting research areas into how do we get these agents, once we train them, to dynamically adapt their behavior based on players. And I think that's where we really want to ultimately end up.
Good. Thank you.
Yeah, thank you. Oh, I guess no more questions. Yeah, thanks everyone for coming.
Thank you very much. Yeah.